Very well. So let us continue chapter 9. So far, we talked about probability. We talked about counting. Now we're going to talk about permutation and combination. So let us write down these two definitions side by side. Chapter 9, 9.3, permutation and combination. Suppose we have n objects. The arrangements, ordering of those n objects is called permutation. So the arrangements or ordering of n objects is called permutation. It happens that the permutation of n objects is denoted by n factorial. It is equal to n factorial. It means that you take n, multiply by n minus 1, multiply by n minus 2, subtract 1 at a time, times 2 times 1. So this is called permutation of n objects. Times 2 times 1. Now I expect you to ask, what if I have n objects and I'm selecting our objects out of those n objects and I want to put those n objects in order? So the permutation of our objects out of n objects is denoted by P of r objects out of n objects, which is equal to n factorial divided by n minus r factorial. Okay, there you go. Give us an example. Suppose I have 3 letters. 3 letters A, B, C. And I ask you, how many 2 permutations are available? How many 2 permutations are available? Well, you might say that, hey, if I follow the formula, I have 3 objects. It means that I'm finding 2 permutations out of 3 objects. So it means that you have 3 factorial divided by 2, 3 minus 2 factorial, or 1 factorial, which is equal to 3 times 2 times 1, or 6. Okay, let us take a look at this. How many arrangements, ordering are possible here? I'm taking 2 of these at a time, and order is important too. So first of all, I have AB, then of course I have BA. Then I have AC, of course I have CA. Then I have BC, then I have CB. As you can see, 1, 2, 3, 4, 5, 6 permutations are available here. You also might be interested in, okay, what if arrangement or ordering is not of big concern? It doesn't matter if A comes first, B comes second, or if B comes first, A comes second. Do we have a name for that? Do we have a formula for that? Yes. We call it combination. The combination of our objects out of n objects is called combination, and it is denoted by, what do we do usually? We write the combination of R objects out of n objects. We usually put that inside parentheses R out of n, and the formula is we get to rid of all of these arrangements, orderings, repetitions. So it's going to be n factorial divided by n minus r factorial, and it is multiplied by r factorial. This r factorial is actually all of these repetitions here. So we introduced two formulas, one for permutation, and the other one is for combination. So if we get back to the previous example, and I asked you, hey, you have three objects, A, B, and C. How many two combinations are possible? How many two combinations are available? Ordering is not important for us. It doesn't matter if A comes first, B comes second. If B comes first, A comes second. AB and BA are the same thing. The ordering is not important. This guy considered as one object. AC is equal to CA, and BC is equal to CB. So how many? 1, 2, 3. Ordering is not important for us. It is 3 factorial divided by 1 factorial times 2 factorial, which is equals to 3. That's the difference between permutation, which ordering is important for us, which one comes first is important, and combination, which ordering is not important for us. Okay, we have some nice formulas. Some interesting relations, you might say. Example. The example says, well, show that for all n values greater than or equals to 2, we have the permutation of 2 objects out of n objects plus the permutation of the arrangement of 1 object out of n objects. If you add them together, it's equal to n squared. Okay, perfect. How do we prove that? Prove. On the left-hand side, remember that the permutation of R objects out of n objects, or the arrangement, when you take R objects out of n objects and you put them in order, follows the formula n factorial divided by n minus r factorial. This is the formula for permutation or arrangements. Okay, so the permutation of 2 objects out of n objects is n factorial divided by n minus 2 factorial plus permutation of 1 object out of n objects is n factorial divided by n minus 1 factorial. Okay. You have 2 fractions. Your goal is to add them together, but they don't have common denominator. What is the common denominator? Let us break this guy down a little bit. The first fraction is going to be just n minus 2 factorial plus, but I'm going to write down the second denominator as n minus 1 times n minus 2 factorial. I'm breaking down n minus 1 factorial. Remember that n factorial is n times n minus 1 factorial. N minus 1 factorial is n minus 1 times n minus 2 factorial. N minus 2 factorial is n minus 2 times n minus 3 factorial, and so on. So, very well. So what is the common denominator? The common denominator is n minus 1 times n minus 2 factorial, but this guy is missing n minus 1. So I'm going to write this as n factorial times n minus 1 divided by n minus 1 times n minus 2 factorial. We're getting back to algebra, plus n factorial divided by n minus 1 times n minus 2 factorial. Now the common denominator is written here. We just need to add the numerators and try to simplify the whole thing. So what are we doing here? They have n minus 1 times n minus 2 factorial, which is equals to n minus 1 factorial. On the numerator, you can factor out n factorial. You get n minus 1 plus 1, which is n. Very well. So if we simplify this, we get n factorial times n divided by n minus 1 factorial. But on the numerator, what do we have? We have n factorial, which is n times n minus 1 factorial times n divided by n minus 1 factorial. You can cancel out these two, and after multiplication, you get n squared. So the first question is, how many different ways can 3 of the letters word bytes be chosen and written in a row? How many different ways 3 letters out of bytes can be chosen and written in a row? In your view, is this a permutation or is this a combination? Also, how many ways five committee members can be chosen from 12 faculty members? Okay. Very well. So since the keyword here is written in a row, it means that it's referring back to permutation. So, okay. 1, 2, 3, 4, 5. There are distinctive objects, permutation of 3 objects out of 5 objects. So we get 5 factorial divided by 2 factorial, which is 5 times 4 times 3, which is 60 permutations. Here it says how many ways we can form a committee of 5 members out of 12 faculty. Is the ordering important for us? Of course not. You're just selecting. You're just choosing. We don't care about arrangement. We don't care which one comes first. It's just a set, including some faculty members. So it is combination. Combination of 5 faculty out of 12 faculty. So you get 12 factorial divided by 7 factorial times 5 factorial. Whatever that number is, you're going to have that combination. You can simplify this as 12 times 11 times 10 times 9 times 8 divided by 5 times 4 times 3 times 2. So you can cancel out these 2. You get 2. You get 22 times 72. 22 times 72. How many? 1,584 combinations. So let's not forget to divide by 2. So it's going to be 11 times 72. And 796. Here we go. So I forgot to cancel 2 and 2 out. So suppose out of these 5 committee members that you're trying to form, out of 12, 2 of the faculty members in this 12 collection says they have to work together. Okay. You're the person who collecting that, selecting those faculty members. Suppose, example, suppose in previous example, 2 faculty insist of working together. So how many ways 5 committee members can be chosen? How many ways 5 committee members can be selected out of 12 faculty members. Very well. What do we have here? We have 2 options. Well, the first option is considering those 2 faculty members or just ignore them. two options. Considering those two faculty members in this group, or just ignoring them, ignoring those two faculty members in this group. So if I consider those two faculty members in this group, it means that I already have selected 2 out of 5. I already have 2. So we already have 2 members. How many left? 3 out of 10. So it's going to be 3 out of 10, or translates into plus addition. Ignoring those 2 faculty members, it means that we are selecting 5 members out of 10 faculty members. It means that we only have 10 faculty members. So plus 5 out of 10. So we can calculate these. We get 10 factorial divided by 7 factorial, 3 factorial plus 10 factorial divided by 5 factorial times 5 factorial. If you calculate this and find the result. There we go. So let us introduce Pascal's formula. Theorem. Pascal's formula. It says, well, let R be less than equals to n, then the combination of R objects out of n plus 1 objects can be broken down into the combination of R minus 1 objects out of n objects plus the combination of R objects out of n objects. Okay, so how do we prove this? By using the definition. Proof. What I'm going to do, I'm going to use the definition, find these 2 fractions, add them together, and get to the formula on the left-hand side. So on the left-hand side, what do I have? On the left-hand side, I have n plus 1 factorial divided by n plus 1 minus r factorial times r factorial. I want to show that this fraction is equal to the sum of these 2 fractions, n factorial divided by n minus r minus 1 factorial times r minus 1 factorial. Plus, here you have n factorial, n minus r factorial times r factorial. So I'm going to just try to take common denominators between these 2 fractions, simplify them, and show that the sum is equal to this fraction on the left-hand side. Okay, so let's see. What is on the denominator? I have n factorial divided by, I have n minus r plus 1 factorial times r factorial plus n factorial divided by n minus r factorial times r factorial. This guy can be broken down into n minus r plus 1 times n minus r plus 1 minus 1 factorial. So this guy is going to be n factorial divided by n minus r plus 1 times n minus r factorial times r factorial plus, now I have n factorial divided by n minus r factorial, n minus r factorial times r factorial. Well, okay, so I can multiply the numerator, the denominator by n minus r plus 1 to create the exact same denominator here. Okay, perfect, almost there. So this guy, one denominator, n minus r factorial, n minus r plus 1. No factorial here. Okay, and on the numerator, if I factor out n factorial, I get n minus r. Here we have, let me see, plus 1, and then, okay, now we need to simplify the whole thing. This guy is equal to n factorial, n minus r plus 2 divided by, let me see, and is everything okay? Let's double check the whole thing, n minus r plus 1, n minus r, n plus 1. Okay. And here down, I get n minus r plus 1 factorial times r factorial. Very well. So let's see what we can do here. We have one extra one here. Let's take a look at this. Oh, I forgot this guy is r minus 1. That's why. R minus 1 factorial. That's the reason. That's why our calculation has missing elements. So this r factorial is equal to r times r minus 1 factorial. So we have to multiply this guy by r minus 1 and r minus 1. Times r, and down here I get r minus 1 factorial times r. Okay. Right. That makes sense. There was something missing that causes trouble here for us, so we're going to fix it. Okay, now here you have plus r, n minus r plus 1, and we cancel out these two. Perfect. So we left with n plus 1, which is n plus 1 factorial, divided by n minus r plus 1 factorial times r factorial, which is equal to our left-hand side. Binomial Theorem. Binomial theorem says, well, if you have a binomial, a plus b, and it is raised to n, this can be written as the sum of, well, the combination of k elements out of n elements. K starts from 0 to n, 0 to n, a raised to n minus k and b raised to k. Well, the expression is going to be, if k is equal to 0, we get a raised to n. When k is 0, we get a to n. Plus, if k is equal to 1, we get 1 out of n, a raised to n minus 1, b to the first power, and you continue this process. And finally, when k is equal to n, we get b to the k. Have I seen this before? Of course. Think about a plus b to the second power. Remember that this guy is equal to a squared plus ab plus ba plus b squared, or a squared plus 2ab plus b squared, which follows the exact same formula. It is equal to the sum, k starts from 0, and your n is equal to 2, a raised to n is 2, 2 minus k, and b raised to power k. So when k is equal to 0, what do you get? You get a squared plus, and write down the combination here, 0 to 2, k out of 2. Then one object selected out of 2 objects. 2, a raised to 2 minus 1, b raised to 1 plus, when k is equal to 2, 2 out of 2 is equal to 1, a to the power 0, b to the second power. The same formula. Well, okay, what's the use of it? Let's go over one interesting example here. Example. It says the sum of k combination out of n combination when k is 0 and stops at n is equal to 2 to the power n. So this guy can be written as 1 plus 1 to the power n, which gives you a equals to 1, b equals to 1. Well, if you follow the formula, it says, hey, I have 1 raised to power n plus 1 out of n, 1 raised to n minus 1, b raised to 1 plus dot 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 1 raised to power, this is n minus k, to the power n. So if you look at the summation is going to be the summation k starts from 0, stops at n, k out of n, 1 raised to n minus k, 1 raised to k. But these exponents are not important. 1 raised to any power is equal to 1. So you can just ignore these. K starts from 0 and stops at n. So A is equal to 1, B equals to 1.